John, I think we'll start maybe 4 or 5 minutes after the top of the hour just to give some people time to roll in.
Sure. Could you do me a favor and just explain what our company does to the people who are not familiar, just in a sentence or two?
You bet. I even have a slide for that.
Okay, great.
Then I'll give you the opportunity to fill in any gaps in my explanation.
Yeah, I won't use it to sell. I'm guessing there'll be some faces that will be coming in from Norway and other places that may not have any idea who we are.
Sure. And we're live now, by the way.
Excellent. I do see lots of familiar faces or names on the attendee list.
All right. Well, it's the top of the hour. We're just going to wait a couple more minutes to let some stragglers roll in, and then we'll get started. I see the attendee number keeps going up, so we'll just keep an eye on that till it seems to stabilize.
Sure.
I see Adam Chin there at the top of the list, alphabetical order.
He's just here to heckle me.
Yeah, he'll be the only one muted.
Yeah.
Okay, just about one more minute, then we'll kick it off.
During the Q&A, are you going to post the questions from the people that are submitting to the chat, Graham?
Yeah. I'll do a little housekeeping at the start and explain where people can type their questions in, and then we'll be answering those at the end.
Glad I got an extra large coffee today.
You don't have an assistant to come refill it, eh?
Oh, I am my own assistant.
Yeah. All right. Okay. So I think we're gonna kick this off. My name's Graham Helfrich, and we have the pleasure of John Thompson presenting today. And the topic is going to be unlocking production potential through rate transient analysis. We're going to do a little bit of housekeeping, and there's about 300 people registered, so we're going to see more people coming in. Now, just so you know, everyone is muted except for the presenter, John, here. But we do encourage people to ask questions at any point through the presentation. By typing it in, there's a Q&A chat window that you can find in the Teams thing. I think it might be up at the top here. So at any point, just type in questions there. And if it's a really easy question, I might respond there potentially, or if it's tough, I'll leave it for John at the end. But we'll review all those questions at the end. If for some reason there's lots of questions and we run out of time, we'll do a follow-up to everyone after with those answers as well. So this should take under an hour, and we are recording. So everyone who's registered is going to get a copy of this after. And if you have a colleague who can't make it, then you can forward this on to them and they can check it out as well. So I just want to mention that this webinar is hosted by Whitson. So a little bit of background about Whitson, which is where I work. It's focused on a web-based engineering software called Whitson Plus, and it really focuses on automating polymer pressures, PVT, rate transient analysis, decline. And free for our Whitson software partners. And then there's a few kind of theory courses that are going to be coming up. It looks like they've actually already happened, but these are recorded. So again, see what's coming up at whitson.com/training. And then these sorts of webinars, we like to do these and invite industry experts, people like, David Fulford, of course, John here today, Curtis Whitson, lots of people like this. And it's just a way to give everyone a platform and share some of the experience and knowledge that these people have and want to share. So we appreciate that. Now, John Thompson, he started with his mining engineering degree from Queens, and then later got his chemical engineering degree at University of Calgary. By the way, both John and I are in Calgary right now, so hi from Calgary. So the main thing that John's doing now is he's the co-founder and president of Saga Wisdom, which is really focused as a digital education platform for the energy industry. I'm going to let John talk about it a little bit more, but the content that Saga has really grown from just, for example, rate transient analysis well beyond that. So I know there's so many people on the call who are already Saga Wisdom partners. So I'll let John fill in the gaps on that. Now, John has authored 19 papers, mainly focusing on, well performance, production, forecasting, stimulation, well spacing, things like that. Now, John and I actually worked together back at Fiquet Associates and in Calgary here, and that's where he was one of our primary rate transient analysis instructors, focusing on unconventionals. And through all that experience, he's analyzed thousands of wells, mainly focusing on, again, tight and unconventional ones all over the world. For 2 years, or maybe 3 years, John was the chair of the SP Reservoir Evaluation and Production Optimization Special Interest Group here in Calgary. And then a couple of years ago, John won a service award for his contributions to the society. So with that, John, I'm going to shut up and let you take it away. And again, fill any gaps in on Saga if I miss anything important, please.
Sure, will do. I appreciate the intro. Hello, everybody. Really appreciate everybody tuning in today. I figure I'll start by just continuing or finishing Graham's thought there. What Saga Wisdom is a cutting-edge digital learning online platform. allowing students, engineers, and geologists predominantly, mostly working at E&Ps, but also service companies, access to all the training course content that you would want to fill your full needs, curriculum needs for upskilling yourself to get that next job or to become a more integrated subsurface technical professional. You'll see that we feature courses from Whitson here with my friend Matthias Carlson. You'll recognize, those of you on the call will also recognize the other leaders in reservoir engineering globally, Jorge Acuna, Chris Clarkson, there's my colleague Dylan, Dave Anderson, but we're continuing to build out these courses. And just to give you a little sneak peek of what these things look like, so you can see the platform as I scroll ahead. There's that beautiful Matthias Carlson teaching away Whitson's RTA stuff. So the transcription is interactive. You can jump anywhere where you want, and it makes learning very efficient and convenient for wherever you are. And that's really all I wanted to say about it. If anybody had any questions about that, you know how to reach out to me, hopefully. If not, I'll provide contact at the end. Moving into the presentation for today, let's get this slide show going. Oh, sorry. Wrong. This is what I meant to do. There we go. All right. The title of today's talk is Unlocking Production Potential Through RTA. My name is John Thompson. I'm a reservoir engineer and have been in the industry for about 20 years. My focus has been on RTA with a real emphasis on unconventional reservoirs. I've got a few objectives for today's presentation. The first is to show you folks how RTA can be used not just for creating production forecasts from existing production data, and useful for reserves, but also how you can use it as a screening tool to identify some unhealthy wells that have production uplift potential, and then using RTA as a tool to quantify the uplift potential possible. Case studies are going to be featured, a couple case studies to talk about what a workover might do in a certain scenario for achieving production uplift, and also playing around with artificial lift, going for, say, a rod pump to an ESP, what would be the potential benefits of doing that. The other is to just eliminate the notion that RTA is a reservoir engineer's toolbox or toolkit, and to say, hey, listen, completions engineers, production engineers out there, you've got some utility for this particular tool as well. It's not hard. Please don't be intimidated. There have been massive advancements in computational efficiency in user interfaces through tools like Whitson Plus. So, please recognize that this tool can be helpful in performing some of the duties you're expected to do within your asset team. What is the concept of RTA in a nutshell? This is stolen from my colleague David Anderson. It's both the science and the art of extracting useful information about the reservoir completion and production operation based on interpreting data, and that's the analysis and modeling of continuous flow of the well, and that's rates and pressures. And typically in RTA, we're looking at resolution that would be daily rate, pressure, time data. And so in the particular example in the figure below, you can see that oftentimes what we did historically for the past 80 or 90 years is looking at really just production rate declines from wellheads in the absence of flowing pressures. Well, it's really hard to know what's going on if that well is rate restricted or choked back. You can see the red data series here. For those of you that are not colorblind, you'll see that the red series here is rate restricted, and you can see that the flowing pressures are dropping at this time. Well, that means that the reservoir signal really is contained in the dropping of the flowing pressures, and between the rate and the pressure, what we do in RTA is we do flowing pressure normalized rate declines, or the reverse flowing. The corollary would be the inverse of that, and from that bulk information, along with some basic understanding of geology, we can really infer and elucidate what's going on in the reservoir for purposes of not just forecasting but development decisions, like well spacing. So I'd mentioned a couple other stakeholders that should be interested in the field of RTA. Well, the primary one, of course, being reservoir engineers, as indicated by the blue icon person here. I'm going to keep these color codes existing throughout the presentation so you could see when we introduce people like the production engineer in green and completions engineer in red. But what you're looking at here with this quintet is really a simplistic overview of what would comprise an integrated asset team, primarily those teams that are working tight unconventionals throughout the world. The value of data, let's talk a little bit about the history, and I alluded to this a little bit before on just looking at production rates alone. For over 80 years, a man by the name of J.J. Arps in, I think, 43, came out with the idea of using analysis techniques. We're talking traditional decline curve analysis, which is really an empirical or math-based technique, just using a series of hyperbolic curves with some rules of thumb. It was useful for forecasting wells in the absence of having any understanding of the geology or the flowing pressures. And that has become the incumbent language of communicating forecasts for the purposes of reserves, for the valuation of companies and their assets. Well, now, you graduate a little bit later, you introduce that red completions engineer, and as soon as you start to layer in more data, you get more insights. And in this case, if you added the flowing pressure information, typically this is at the wellhead, because most people don't invest in downhole flowing pressure measurements. But with surface pressures and an understanding of the wellbore and the well schematic, you convert these things to bottom hole, and you can start getting a better understanding of what the forecasts on these wells will be. And you can also start to evaluate things like completion effectiveness. In other words, the very famous linear flow parameter, A root K, which is how tight fractured wells are evaluated in early time. Then if you take another layer of data, and now we're talking about the basics of the reservoir, we're talking rock properties and fluid properties. These are established from things like petrophysical log analysis and fluids analysis in the laboratory. You can start to get a very good and even further improved sense of the forecast and reserves, but you can also start to establish basic bulk reservoir performance parameters and properties for the purposes of well spacing optimization and other field development planning. And in this presentation, you're going to see how it can be useful also for further identifying wells that may be unhealthy that have production uplift potential. And then you'll see the introduction of that icon here in green, which is the production engineer. So let's first take a look at a triangle that I whipped together back in 2016 for a presentation that I gave at the Calgary Petroleum Club. This is really just a high-level overview of where RTA production modeling might sit in what I'll call the pyramid of techniques that can be used for the purposes of forecasting and reserves, in this case also development planning. The bottom is that rate time decline curve analysis. This is traditional DCA or ARPS. This is the most heavily used methodology because it's super fast. People can do can roll up forecasts for M&A decisions or acquisitions and divestitures decisions very, very quickly. They can establish type wells, or what often are referred to as type curves, somewhat inappropriately, so that they can get a sense of where any of their wells are in relation to sort of statistical output for how wells are performing in the field. That's an empirical technique. An empirical, again, just meaning math. Another one would be introducing rate pressure time DCA. The folks over at Netherlands Sewell, the late Chris Tucker, started doing these types of techniques along with my colleague Dave Anderson at Fiquet back in 2011. We're publishing papers on improved forecasting estimates with rate pressure time analysis. But this was still in the absence of having any understanding of the petrophysics of the reservoir, etc. Then you get into RTA, where it may sit. Now, the A in RTA, of course, we all know stands for rate transient analysis. A is analysis. Please don't ever call it RTA analysis. We don't like saying the same word twice. But where RTA sits in here is also some fairly simplistic production models. Those production models are available in commercial software, and now they're remarkably efficient, both analytically and, most importantly, numerically for those complex multi-phase flow systems or reservoirs. Then what we would often refer to as simulation, which is just more complex or advanced production modeling. These are black oil models or modified black oil models in tools that you would have like CMG, or kinetics like SLB, etc. So the more time you spend, the more insights can be derived typically, but of course, efficiency matters. And that's where RTA can sit as a practical tool in this pyramid. So we should start to understand a little bit about flow regimes. Now, for the people on this call, I think most of you, from what I could see, I recognized a lot of you. You have reservoir engineering backgrounds. You have used tools like RTA. This isn't going to be brand new science, introduction theory for you, but I still think for the few people, I've got to kind of go through this. Transient flow. This is an infinite acting flow regime on tight fractured reservoirs. You're going to be dealing with linear flow as the first clearly identifiable flow regime that you see observable in your daily rate pressure time data. What that means is that there's no physical or no flow boundaries are being felt. The best analogy that can be provided again from my buddy Dave Anderson is you take a pebble, you throw it into the center of a pond, the ripples that originate from the splash, they of course propagate towards the shore face, and that is a very good conceptual description of what transient flow is. You haven't felt any boundaries yet, and that's the useful for determining near well parameters. That's essentially what the pressure wave is doing as it goes from the well or fracture face sweeping into the well, through the diffusivity equation. And so that's what's being used to sort of establish or elucidate properties like permeability, frac length, skin, anything that would be considered near well. Oftentimes in multi-fractured horizontal wells for operators that are exploiting ultra-tight unconventionals, you'll see communication between frac to frac. So no flow boundaries, or maybe you hit things like faulting or other things that cause a transition or an end to linear flow. There's information contained in there. A lot of the work of Clarkson and other authors have tried to investigate what can be learned from these types of flow regimes, if you want to call this the transitional flow period or regime. And then there's boundary dominated flow, which conventional reservoirs usually the bulk of production data for more conventional or high perm reservoirs or smaller reservoirs, usually you can establish this final flow regime. That's when all the boundaries are felt. The analogy is that all of those ripples have hit the ripples have started to hit the shore face. The well is now in tank-like or depletion mode, and it's a wonderful flow regime because you can calculate things like the original gas in place or oil in place, hydrocarbon in place volume. If you establish this, say, for an unconventional reservoir, the beautiful part of that flow regime is that you can reverse calculate your petrophysics. So if you think you've got a good handle on porosity and saturation, initial saturation, you can start to figure out what all operators want to know, which is what is the effective penetrated frac height. To take a quick look at a cross-section and plan view look of the previous conceptual description of transient and boundary dominated, taking a look at cross-section view, you can see that when each data series is a different point in time, this is temporal information, and you can see a declining flowing pressure on the well. And you can see that with each time series, the inner being time 1 and then time 2 and then time 3, as we propagate out, we're investigating deeper into the reservoir, getting those reservoir parameters of permeability, frac skin, etc. And then when we hit the boundary dominated flow on the edges of the reservoir, you're starting to get into original in place volumes and productivity index. The workflow for RTA can be overly simplified by breaking it up into a series of analysis techniques, which is the A in RTA again, and production modeling. But here I'm just talking a little bit about what is needed in the initialization of the well examples, or what you would call the problem setup before we start to investigate the data, interpret the data. There's some basic things that we need. We need the petrophysical parameters. I mentioned initial saturation, porosity, and pay, along with the initial reservoir pressure. And you'll notice that PI, or initial reservoir pressure, comes into the bulk of the plots in RTA. Usually it's PI minus something plotted against something else. Pretty important parameter. But we can establish this from disparate sources of oil field data and test data, which includes but isn't limited to things like diagnostic fracture injection tests or DFIDs. The fluid properties in PVT, what Whitson is world renowned for, of course. We just need some basic things from the PVT for the fluids properties, talking about saturation pressures, or it's a bubble point if it's an oil well, a dew point for a gas well, and just gravities like oil gravity, gas gravity. Very little information is needed. If we don't have it, we can make an educated guess and still conduct our workflow. Measure bottom hole pressure, of course, is critical for performing RTA, but we can have just surface pressures, and we can convert those pressures using well schematics or tubulars so that we can get to the bottom up to a true analytical value for the bottom hole pressure. Of course, Whitson has really spent a lot of time trying to make sure that those calculations are as rigorous as possible so that you have the most accurate and reliable value at the bottom of the well, which is where all the math is being used for the reservoir engineering calculations. Analysis can be broken into a series of straight line analysis techniques and type curves techniques. Here, a type curve is a dimensionless representation of a well reservoir system where you position the actual existing well data through a type curve, and you're using that to establish both the transient and boundary dominated side. So we're getting all those reservoir properties and the volume in place from that. And then the straight line techniques are super useful because you can use them to compare wells against each other, and their relative performance differences are really what tell you, give you insights about how wells are performing or underperforming and how to make those development decisions. Flowing material balance analysis will give you oil or gas in place, in this case, gas in place. And for linear flow analysis, again, this is the world's most popular plot for the analysis of tight fractured wells. So we use that to get linear flow parameters, which is almost like a linear flow capacity, if you will, to give you the ultimate potential for deliverability for the well. And once that ends, then that's where we really start to wave our arms and start to explain what's actually going on in the well. RTA, this is where I spend most of my time for production modeling. This is taking a look at a plan view of the well. This is where we start to come up with descriptions that are can match the available production history. When you do get a successful history match, meaning that you might use the oil rate, look to your model, look to the properties, and start to play with those properties until you regress the model solution through the actual data. At that point, you have a history match, and that just means that's one permissible or one possible description that satisfies a match. It's in the solution space. It doesn't mean it's exactly that, but you start getting into these exercises, and that's when you start to have a useful tool in the way that I will demonstrate in future case studies of being able to understand if the well has more it can give you, irrespective of the fact that maybe this description isn't exactly what it looks like in real life. And so once you have a history match, you can forecast, and that's where you can forecast at different well spacings, and you can play around with field designs and have a very defensible, defensible or audit trail based forecasting methodology for reserves evaluation. Now, I mentioned the most famous plot is a linear flow plot. In its simplest form, this is what you're looking at. So you draw a straight line through your data, and you've got an intercept here. What can we learn? Well, the data is already being prepared on a plot of 1 over the production rate versus square root time. We can introduce superposition time functions to make this a little bit more mathematically complex, but effectively what we're trying to do is linearize the data so that we can make interpretation of the data easy by drawing straight lines through it. The power of this particular plot for completions engineers especially is that they can evaluate various wells with different designs to understand what their slopes and intercept differences look like. The intercept is a catch-all term for all the apparent damage on the well that exists beyond the Darcy flow equation and the material balance. And the straight line, of course, is the bulk product of the cross-sectional area created from the stimulation and the square root of permeability. So a little bit about what was in there to begin with and what we achieved through the completion in that frac area. You could have a situation here on the side where you've got that intercept that's caused by a bunch of linear flow flowing into fractures that are unpropped, where there's very limited conductivity, or maybe there's a film of water and creating a fracture face skin that the oil or the gas has to migrate through in order to get into the fractured well system up to surface. All of that can give you intercepts or damage. The propped region, however, highly conductive regions could be the other part that's infinite conductivity that's giving you, contributing strongly to your flow response. The concept of a reservoir doctor is one you want to like this. This is an a topic I should start by something that Dave and I conceived together back about 8 years ago. Dave actually presented a version of this at an URTEC technical luncheon several years ago. But really, this is the theme of the presentation here. It's how to use RTA as a screening tool to identify if there are well performance issues that are causing wells to perform less than they could be. And so this presentation is going to be used to high grade these wells, identify them, high grade them, and run little tests to see what these wells could be giving us if we could fix the problem. Here's an example that we've presented in the past. It's a 2-well example, and looking at just rate time alone, and there's that reservoir engineer in the absence of the production and completions engineer who looks at these 2 wells and says, I don't know, this is tough. Which of these 2 wells is the better well? Well, without those flowing pressure data, it's not an easy exercise. Maybe to an experienced eye you can tell, but it's maybe not to someone new to the field. Well, if you take those 2 wells and then you layer in the flowing pressure data and you start to do rate normalized flowing pressures, you can start to see on those square root time plots or modifications of those square time plots, we'll call them linear flow plot analysis, you can start to see that there is a discontinuity on a well too that becomes quite apparent when you start plotting the data in this form. And really, it's just the angle in which that we're looking at the data in the way in which we've described the analysis plot. We can actually pop out data to show that, hey, after 2 months, there's a loss in well performance or productivity. What happened? Well, in this case, there was an opening of a choke, and there was a stress impact, and there was a complete loss in productivity. So that's the value of analysis or a linear flow plot that the completions engineer could use. But from this point on, we're going to get a little bit more advanced by layering in an understanding of the basics of the geology and the PVT. So this is a real case study that I worked on after I'd finished at Fiquet, but before I'd started at NCS Multistage with Dave. This is a Canadian tight gas well example. This is the Falher, actually, for those people familiar with the Western Canadian Sedimentary Basin, which is like one of the more popular tight fractured reservoirs in Canada. And the problem in this particular case is that there was a mechanical flow restriction somewhere in the lateral. And the symptom was observable when performing RTA. There was an inconsistency between the rate pressure response. How did we diagnose it? Well, first with RTA, and then later the prescription is to investigate the well with the downhole camera and see if it's something that we can fix. And so the prescription following that would be, we're going to have to do a workover. So this operator had hired me to look at a number of wells and to high grade the wells that probably needed a workover. This was the history match. In this case, again, it was a gas well, as indicated in the beautifully monotonically declining red data series here. And then we had the calculated pressures, calculated from wellhead, from casing pressure. And the best history match that I could achieve by playing with my model and the model parameters is indicated in front of you now. So when I was a younger practitioner of RTA, I would have said this is as good as the model can get or my match can get, and I've got another 50 wells to history match. I'm just going to proceed with this and create forecasts around this and submit those for my reserves manager or reservoir engineering manager and say, I'm on to the next well. But after doing this exercise for several years and seeing countless wells modeled poorly, I started to get frustrated because I started to think, is it because the models are too simple and that's why this isn't working, or is the data trying to tell me something? And so over the course of several years, I started to recognize that the data was really, in fact, trying to tell me something. So when you see the discrepancies between your model pressures and your calculated pressures, again, when using production volumes to do your matching exercises, you'll see that what the model was trying to do to reconcile the match was say we needed huge changes in pressure to capture small changes in production rate. So what is that trying to tell us? Well, before we move on, notice that there's a 54% error in the match, and that's the best I could do. Well, we need to understand the theory of inflow performance relationship, or for gas well, absolute open flow curves, same thing. And what that means is that when we are in a period of high percentage drawdown, which was the previous assumption in the previous example, we were assuming 90% drawdown by history matching, trying to history match at these very low flowing pressures. We can see that the history match would be fairly insensitive. If we're making large changes in pressure, it's not going to have a big impact on changing the production rate. And I think that's really what this was trying to tell us. It's like trying to make these huge leaps in pressure to reconcile these small changes in rate, and it's not working. So a consistent response would be a small change in pressure has no change in rate if we're high drawdown. And that was where we thought this example was. But an inconsistency would be big change in pressure, no change in rate at low percentage drawdowns. Okay, so let's start to learn from that theory of IPR curve work and percentage drawdown and apply it to this example. Well, if we could do one of two things with percentage drawdown, one is you could lower the initial reservoir pressure and leave all your calculated pressures alone. But that theory was discarded quickly because this operator had lots of external evidence, test data and other data to show that the pressures in fact were high. So they said, you're not allowed to play with initial reservoir pressure. I said, okay, but what if I calculated the bottom hole pressures differently? Or what if we added an additional pressure loss term, in this case of 2,000 pounds, to every single calculated flowing pressure? And you could say, well, flow rates are changing. Isn't the pressure loss a function of the rate? And so like, yes, to a point, but the thing is across an orifice meter, you'll see, I think through the theory of supercritical or supersonic flow, that you can arrive at a constant delta P through an orifice at a given set of, at a given rate and set of pressures, one on one side of the orifice, one on the other. Anyway, you can, it's defensible to say that you can achieve a constant pressure loss term across all of the data. And the evidence is quite simple. If you were to perform that calculation, you'll see that you've got a, with a constant delta P of 2,000 PSI above what we had previously, it's a flawless history match, 1% error. So now if you're saying, okay, well, this is diagnostically valuable, what do we do now? So let's just take a look at where we thought we were. We originally assumed the theory of percentage drawdown said we're high drawdown. Now the models with that extra 2,000 pounds of pressure loss suggest that actually we're probably down here. Okay, well, that's a big gap. That means this well, if we could fix this problem, could give us a little bit more. What could be happening? Well, dropping a camera in the well, we can see in reality, there's a whole bunch of things that can be happening in wells that we didn't know about. Here are a few different examples. One would be when we're milling, and in the case, you mill right through the casing, not just through the plugs, but in a plug and perf, but you can collapse your well bore. That's not going to be very good, and that could cause an additional pressure loss or mechanical flow restriction. Sand cleanout is a very common one, of course. We frack these wells with enormous amounts of sand, and when we turn these wells on to production, we often have sand in our wells and all the way up to our surface equipment. Very, very common. And so sand cleanouts are a common exercise. In this particular image, you've got a ball drop completion where the operator just kept dropping balls because they didn't have that diagnostic response during fracking that the ball had found its seat and opened the sleeve. Well, look how many balls they were dropping to try to find their seat, and you know it's parted the casing. So there's many other photos that I could show you, but these are all the real things that can happen in wells that the reservoir engineers or the other engineers on the team can't really know. They can't see what's going on. All they have is their data at surface. So let's say it was a sand clean out, because that's a common one. And of course, there's other evidence. If you started to see sand returns at surface, that would be a bit of a tip off. But RTA could say, okay, well, I think we need a sand clean out. What's that going to cost us? That's going to cost us a couple $100,000. Well, let's run a camera in first just to make sure. Okay, well, the camera's going to cost you 50,000. So you're into this well for remediation for about $250,000. Now the question is, if we can get rid of that 2,000-pound pressure loss and truly clean it out, what's the uplift potential? What type of wedge production can we get? Okay, well, this is using a production model, dropping that flowing pressure back to 90% drawdown condition, removing the restriction. You can see that you can get an incremental almost BCF of EUR out of it, and then you could do you could properly calculate the economic benefit of accelerated reserves recovery as well. And so maybe you're going to get $1 million back of net present value, which will more than offset the $250,000 you need to perform the workover. So for case study 2, it's a U.S. tight oil well. This is actually in the Bakken, Three Forks in the Williston Basin. This is a Bakken well. This particular operator, and then here's our guy, here's our completions engineer, production engineer, and reservoir engineer once again. This was using RTA to do, we'll call it artificial lift optimization. So how to use RTA to figure out what type of pump to land. In this case, they were on a rod pump. They went to ESP. Following the change to ESP, the well lost productivity, even though it was a successful outcome in terms of increasing rate. RTA was used to identify that. And in this particular exercise for future wells, to mitigate any type of productivity loss, the idea would be like maybe next time we'll use a smaller pump. And if we did that, maybe we get an extra 15% improvement in EUR. Apologies for the lack of legend on this one, but hopefully we can see on the screen. We've got an oil well that's fairly constant rate for the first year of production. That's because oil pumps usually don't go much higher than 500 barrel a day, 400 or 500 between the water and the oil rate. So it's rate restricted because of the artificial lift type that was being selected. But after a year, the production engineering team said, let's move this thing to an electric submersible pump or an ESP. You see that kick in rate going from 500 barrels a day after the ESP is installed to 1,000 barrel a day. And then you see that nice decline again. And you'll see that the GOR is unaffected throughout the entire operation. It means that it's an undersaturated oil reservoir. And even through these changes in the operating conditions, we still aren't really below bubble point significantly because the GOR is fairly flat. So at least that's not something that we're dealing with, which Permian operators are, of course, often having to face. Okay, so at 2,600 pounds of flowing pressure, we're getting 500 barrels a day. At 1,000, we're getting 1,000 barrel a day. Okay, so the engineering team thought this was a success. Like, good job for us. Look what we've done. But it could have been better. So here's what the RTA model is trying to tell us. History match the data when it's a rod pump. To calculate these pressures, you usually use liquid levels or joints to the liquid level on the annulus side, and then you do your pump intake pressure calculation to calculate the bottom hole pressure. That's why the data is a little bit more scattered and not as beautiful as when it's on electric submersible pump, when there's an actual intake pressure being measured in the bottom of the well. So that's just the data quality issue. So the model suggests, based on the history match of the first 10 months of production, that to get that 1,000 barrel a day oil kick post change, we should have had 1,850 psi, not 1,000 psi to get that rate. If we were to, but we actually got 950 psi, which we know reliably because we had a downhole pressure on the pump. So what's going on? Like, why did the pressures not match down here? Why are they matching up here? It's like, well, there's productivity loss, and that's what the model's trying to tell us. So this operator concluded that, well, you know what? We actually used a massive ESP. Maybe we used too big of an ESP. Maybe we dropped those flowing pressures too fast, too quickly. And yeah, we got the rate up, but the rate could have gone up a lot more. We could have had a sustained higher rate production if we used a smaller pump. And so that's what that operator decided to do on future wells. Now, we could play with the forecast and say, what if we never had that productivity loss? What if we used a smaller pump one that could still get us 1,000 barrels a day, but we wouldn't have that sharp decline. Well, the upside of this well, if we didn't have any productivity loss from effective stress effects from the way in which we were operating our well, maybe we get an extra 15% improvement in EOR plus accelerated reserves recovery. So this is a way to use RTA as an autopsy, a post-mortem, a look back on a well of what we've done. In this particular case, there's no remediation possible. This well has lost its performance, but on future wells, let's not repeat the same mistake. So to conclude with this presentation, every well should have a clearly stated performance expectation, not just a production target. Most wells fall below expectation, and because there's a million things that can cause wells to lose productivity through time. We want to continuously monitor our wells with tools like RTA to make sure that we can get the most out of our PDPs, our wells that are on production. The productivity lots, as I've shown you in the previous examples, it isn't always obvious. So we want to spend a little bit of detective work looking at our well data. And that RTA should be used as a screening tool to identify targets that are low-hanging fruit for production optimization. There's lots of things we can do. The data is free, the time is not, but we do have advancements in commercial software so that we can conduct these workflows faster than we ever have in our careers ever before. So the hope is that, you know, even if we're managing hundreds of wells, hopefully through continuous software advancements and automation, we'll be able to pick these wells out so that we can tell our production engineers and technologists in the field of these problems so they can address them and squeeze more oil and gas out of them. So thank you very much for your time today. I'm open to questions.
John, thank you. It looks like the aliens are beaming me up here, right? Yeah, okay, so we have a few questions. One is back from slide 23, and you might have to share that again. I think slide 23 was the end of the case study, but the question was the rate change at a higher drawdown?
So the rate change was at a higher drawdown. Specifically, the well was at 2,600 pounds. Here, this is a better way to illustrate it. So the drawdown of the well, which is a relationship between the initial reservoir pressure or average reservoir pressure, but for transient systems, it was the same number, and the bottom hole flowing pressure. Well, the whole thing is the original bottom hole, like the bottom hole flowing pressure here is 2,600 pounds, then it goes to 1,000. You can express that as an increase in percentage drawdown to achieve this increase in production rate. However, the model suggests that to achieve that production rate, if there was no damage or no productivity loss, it didn't need to go to that level of percentage drawdown. It could just go to a much lower percentage drawdown to achieve that rate. So what we're seeing here is that is loss in performance or loss in productivity through damage, which could be conceptually considered as an increase in effective stress from the well operation or geomechanics, or in this case, this is a tight fractured well, so a multi-fractured horizontal well. So those fractures are being compressed as a result of the stress on the system from how this well was operated with the larger pump. So if it was more gentle, you could probably still get at or close to this production rate, but they drop pressure so hard, so fast. The theory is that it resulted in a long-term and like reduced like productivity or more, like this well was damaged. You can theorize what caused the damage, and I've given you a good explanation as to what could or is likely going on. But the one thing RTA can tell you quite clearly is that your productivity index and your productivity has changed.
John, on that topic, I think of the word hysteresis. Does that apply to this?
Sure, it does. So hysteresis is talking about elastic or plastic deformation. So in hysteresis, the idea would be like, okay, John, we've damaged the well, but what if I ease up on it and we shut the well in and we let the pressure get restored? Can I restore my fracture properties and the conductivity and the reservoir permeability for systems where permeability is a function of pressure? Um, Perhaps in part, but not fully. And in our experience of analyzing tight fractured wells, you're generally dealing with plastic deformation or permanent deformation caused by stress. These things aren't fully reversible. If they were fully reversible, it would be called elastic deformation. So, unfortunately, in most wells that we have analyzed in onshore North America, primarily, this is not reversible damage. So this is too late. Don't screw up next time, is the message. But yeah, you can sometimes get partial recovery by, you know, pulling off on a well a little bit, letting it recharge. You get some of your properties restored, but it's not generally very good.
Okay. Slide 26, and I'm not sure if that's a different case study, but the question was, what's the main reason for productivity loss and what evidence do we have? Is it the same well or is it a different well than the
Okay.
one we just
Well,
talked about?
okay, so we have two examples in this case, but I can give you more examples. In fact, there's a vacuum Huerta case in here too, but I just, for the interest of time, I didn't present it. The most common effects of productivity loss, in my experience, and there's several, of course, there can be damage in the well. Well, there's damage in the reservoir, there's damage in the well, and these are different and they manifest differently. But say damage in a well could be sand, as I showed in a previous example, coming into the well, and a clean out run would be something to mitigate or remediate the damage that would be caused in a well. Scaling and chemicals can be used. Production engineering chemicals can be used to enhance production, and that's types of damage that could accumulate over time. These things could be modeled in RTA with increasing skin damage through time, which could be the result of things like scale and deposition and other things. There's a myriad of damage mechanisms that can occur. The question is, can we remediate them? And you can't provide prescriptions to things you can't properly diagnose, which is why we use terms like the reservoir doctor. You can't start throwing drugs at a patient if you don't know what the patient's suffering from. So what RTA isn't very useful at telling you exactly what's going on. It can just say, hey, wait, something is wrong. Like there's an inconsistency between what I'm seeing with the rate pressure response. And so maybe I need to investigate that further. What RTA is remarkably strong at is uniquely nailing down percentage drawdown. Because when you're dealing with wells that have changes in operating conditions, maybe short little shut-ins for a couple days because you're installing tubing, or any type of like operation where those rates and pressures have a step change, it's that change in the rate and pressure that allows you to like really hone in and start to understand what the true percentage drawdown is on the well. And that is very useful because that's where you start getting into, could this well be giving me more? And so I can't generalize and say, well, wells lose productivity always this way. Well, that's not true. There's a lot of things. In stress-sensitive reservoirs, these are abnormally pressured plays where the pore pressure gradient exceeds 0.8 psi per foot, or for you people who like your metric units, like north of 20 kPa per meter. Those are the wells that you start thinking about as high-risk candidates for losing productivity based on the way in which you operate your well. And I'm talking about choke strategies and what have you. Plays like the Vaca Muerta, the Duvernay in Canada, the Eagleford, the Haynesville, the Niobrara, these are all stress-sensitive formations. And if you decide that you want to get a high initial production rate on the well by whistling down flowing pressure rapidly, you can cause a loss in long-term productivity, which, you know, those of you who have worked those plays should be very familiar with, which is why they have rate-restricted programs on purpose so that they don't suffer from the losses of, productivity losses from effective stress.
Thanks, John. So I know, RTA, it's almost exclusively used on production data, but the question was, has anyone ever tried applying it to horizontal injection, where you take the bottom of pressure, the injection rate, and try to do RTA on that?
I've never seen RT on that. I've seen pressure transient analysis techniques on that.
Right.
There's injection well test techniques that are becoming quite popular. There's always there's a hat that should be made saying make well test great again. But injection well testing is being used in the Permian on a regular basis, say Endeavor Resources, now Diamondback, because they're doing salt water disposal applications, quite a bit of it. And so they are doing injection well testing and using that data for that reason. The other one, of course, throughout the world is the injection of carbon dioxide into for sequestration. This is carbon capture and storage. This is a PTA exercise technique. These are conventional reservoirs. You don't need rate transient analysis because pressure transient analysis is a more controlled test, higher resolution data. But effectively, it is sort of the sibling of RTA. So if you want to think of it in that sense, yes, we are doing injection pressures and analysis, but we're just calling it pressure transient analysis.
Awesome. One question is about, using public, like monthly data on RTA, and they're talking about 10 years of history, and obviously we don't have pressure data with that, but are there some safe assumptions once you have really long, like 10 years of history, that we could potentially glean value more than just a decline curve?
Yeah, and the answer is absolutely, and that's what you and I did at Phuket, Graham. So if you have low resolution data, you don't have flowing pressures, can you still perform RTA? There are some senior practitioners at Phuket that would have said no, and I always got frustrated because I'm like, well, we can make some reasonable assumptions for the reservoir parameters because we have external information from petrophysical logs. We can populate RTA and initialize our setup with a reasonable understanding of initial reservoir pressure, pay, porosity, saturation, and in situ fluid properties. We don't know what the flowing pressures are, but we could make up a made up flowing pressure profile through the models based response for pressure and say that makes sense. And then what we're doing is using RTA in a volumetrically constrained sense. It's still a physics-based approach where we can figure out the forecast as a function of different, say, well spacing scenarios or reservoir size scenarios. You can't do those exercises empirically in the absence of setting those up. So I would say you absolutely can you can bookend your understanding of your forecasts using a physics-based approach or a physical model, even when you don't have that, high resolution or external data. You do your best guess and you proceed.
Excellent. Okay, here's a good question. What is the minimum amount of well history in terms of time to get a reliable result on EUR with RTA?
Yeah, it depends on the well reservoir system. If you're talking are you talking a conventional well or an unconventional well? But the tighter the rock, usually the little bit more time that you need. The dynamics of the changes during well cleanup can influence, can lengthen the amount of time necessary to try to figure out what's going on. Operators typically for tight unconventionals, they have a flowback program when the well has cleaned up mostly, or at least, the bulk of it, the dynamics of the changes have sort of established themselves. I would say the old answer was 6 months of data is what we needed to do our exercises, but in my experience, I would say three months is probably in most cases is realistic or reasonable. 3 to 4 months. Is usually what we ask for as a minimum. Now, of course, people keep trying to make it to figure out what's going on in 1 month and 2 months. It really depends is the answer. And every formation in the various basins, some you can do in like a matter of a month, and some you need a few months to have the rest of those dynamics settle down. So I know that's not a straight answer, but it is like there's a lot of variability from play to play.
Yeah, like it would probably, in transient flow, it's difficult. If you see boundary dominated flow, a little easier.
Yeah, well, in boundary dominated flow, the benefits are the well reservoir description doesn't matter anymore. Like you have what you need at that point for establishing your volume in place
Right.
and your reserves. Once you get into that, your reserves estimation reliability goes through the moon. Like you're very confident with how these wells are going to behave.
Right. Okay. The question is, frac heights may extend over multiple benches,
Mhm.
some of which have unproductive zones. So how do we get an effective, net pay porosity saturation if we're going to turn it into a single layer model? And how do these single layer models compare to a multi-layer model?
Okay, then you need external information to understanding what those effective prop contributing frac heights truly are. So yes, I understand the pain and frustration of not knowing these numbers going into these exercises, but oil field operators have invested in countless amounts of diagnostic testing, particularly in recent years with time-lapse geochemistry for understanding where frac heights are. There's other forms of tests that can be conducted to determine frac height. In fact, if you talk to your completions engineers, they've got various techniques that are different from reservoir engineering types that are looking at ISIP data to figure out if they've fractured into certain additional layers, lithofacies, or zones. Um, it is not an easy exercise when we're trying to understand fracture height and if we're fully penetrating our targeted interval or if we're fracking into something overlaying or underlaying. This is where the big investment of the decisions comes in. That's where again we have these additional tests. We look for things like interference. We look for diagnostic markers to see if we're getting, H2S could be an indicator that we've gone too far. Water, if you're hitting a water leg or an aquifer and you're seeing a higher water cut, that could be an indicator. These are the sorts of things people are oil fingerprinting and using DNA. I mentioned time-lapse geochem. There's tracers. There's so many things that operators are doing in fiber to figure these things out. It is not easy, and I'm not saying that RTA by itself can do that. In those types of situations, you need an integrated suite of tools and an integrated team.
Okay. I think last question, John. Let me just find it here. Okay. So it, can you use RTA to identify baffles and barriers, just like in pressure transient analysis?
Sometimes, yes. Dave and I actually were always called in. Okay, we're operating in Canada, and one of the most popularly drilled plays is the Cardium Formation, which is very popular in Alberta. And in the Cardium, we would see very good-looking geology or petrophysical logs and very poor performance results. Well, if you had a dipole sonic and you can see a stress profile that could be created, which completions engineers like to look at to populate their fracture models, not production models. They can see from those stress profiles and stress contrasts that there could be a fracture barrier or baffle in place. And when the well performance tells us that we're only getting half of the expected performance from the well, the question could be what's going wrong when we do perform exercises like fracture modeling, and the tools that are out there. Um, when you conduct those, you can see from those studies that yeah, like it looks like we aren't penetrating that fracture baffle or barrier. So there's lineaments or there's strata that are could be several feet thick that you can't punch through with your stimulation. And so let's say an operator is doing a 20-ton per stage frac, which is all you need in those types of plays. Depending on where your well is landed and the completion design decisions, you can't get through those fracture barriers. But you go 40 tons per stage and you land a little closer to the barrier and you pop right through it. These are the types of studies that we used RTA on throughout Canada, and that Cardium is a good example. That it's super common. So I would say, yeah, you start using other tools like frac models, but you also start to use maybe microseismic, which isn't great about telling you where all the propped fractures are. Don't listen to the vendors. Um, but they are very good at showing you that there's no microseismic event activity above a certain level. And that can clearly, where I like microseismic and I don't love it, but where I like it is to be able to see that we aren't seeing any seismic activity above a certain level. It goes really, really quiet, and that's how you know you've got a barrier. Oh, you're on mute. I can't hear you if you're talking.
Thank you. I was just practicing my miming actually, but
Mm.
no. Thank you, John. Just someone did submit a thing and there was a Q&A section. There was one question and I think John answered it. It was just, if an area was acquired and does not have surface pressures, what's the best way to use the well history? And I think you kind of answered that when you talked about using monthly data. It's just you assume a pressure profile, right?
I'll need a more specific question there.
Sure. It says if an area was acquired and does not have surface pressures, what would be the best way to use the rate history without the surface pressures? Okay, and then so I think I'm reading the question again. So imagine a well with 10 years of history and it's missing the first half of the flowing pressures, but in the second half of the well's life, it does have the flowing pressures.
Oh, easily. I use the model to infer what those pressures could have been. So I match on the late pressures and I make up the pressures through the model to fill in the gap, is what I would typically do. And I recognize there's uncertainty with that. And that means that some of the near wellbore parameters couldn't clearly be elucidated or calculated, but I'm okay with it depending on what my objective is. Is my objective a forecast going forward? Is it characterizing near wellbore? The answer is always, what am I trying to do? And so it's fit for purpose application of RTA. But yes, you would fill in the missing part with your model.
Perfect. Well, thank you, John from Saga, and thanks for everyone for joining. Everyone who's registered will get this recording, and thanks again for your time, John, and your contribution to the industry.
Thanks a lot. All right. We'll see everybody later. Have a great day.